Hi everybody, welcome to another lesson on calculus. Today we're going to be talking about something called related rates. And as you can probably imagine, related rates are going to be dealing with speeds. At this point in the course, I hope it's pretty natural that anytime you hear the word rate or speed, you should probably be thinking about a derivative. And specifically, when we're talking about speeds, we're going to talk about derivatives with respect to time. So we're going to be using t as our input variable. Okay. First of all, when we think of speeds, a couple examples that we use on a kind of a day-to-day basis, often ones we use are miles per hour, or a common one in physics tends to be feet per second. And notice that both of these have a distance divided by a time. And so when we have a distance divided by a time, that's where on the bottom, when we take a derivative in these problems, we're going to be taking a derivative with respect to t. And so we're going to have dt on the bottom. And it could be d whatever on the top. It could be dy, it could be dx, could be dA for area, could be dp. Use any variable or letter that you want that represents a certain context. Okay, so first of all, let me kind of explain some of the structure of some of the problems that we're going to see in this section or with these kinds of problems. These deal with real-world practical applications of derivatives. And so anytime we have a real-world practical application, that problem usually doesn't look like a math problem or an equation at the very beginning. Usually what it looks like is a real-world context, which often shows up as a word problem. And so the real-world context problem that we're going to have, I'm going to kind of think about working for a company or being in a business somehow, and somebody comes to you with a problem and says, I'd like you to solve this problem for me. Usually that problem doesn't start out with equations and look all mathy. Okay, usually it looks like real-world context and has real-world units involved and a real-world situation. So your job should be to take the real-world context and to turn it into a math problem that is a bit easier for you to be able to work with and solve. Okay, so in the math problem that you have, maybe it looks like equations, maybe it looks like, for us it might look like using derivatives or whatever. Once you have the math problem, your goal then as a mathematician is to solve the math problem. Okay, that should be pretty straightforward, and figure out what is it that we're looking for, what is it that we're trying to find. And then the problem is, once you solve that problem, you're not just kind of keeping that to yourself. You're usually presenting that or bringing that back to the people who asked you to solve the problem in the first place. So if you work for a company, your boss might come and say, hey, solve this problem. That's great. You got to go bring that problem back to your boss. And so you need to explain your answer or your solution in context as well. And so you need to be able to bring it back to the situation in the real world using the real world units that are there, and usually this all involves kind of writing your answer in a sentence or two at the end, explaining your solution. Okay, so this is a good kind of diagram to think about just word problems in general, but that's going to be applicable here when we talk about related rates as well. Okay, so how do we deal with related rates, or what are related rates? Okay, a related rate is a way to be able to relate, I know that sounds silly, relate one speed to another, or maybe it's multiple speeds together, and think about how different things are changing over time. Okay, so these problems are going to be fairly involved. These do tend to be some of the tougher problems that students see or deal with in calculus. And so because of that, I want to give you kind of a structure, a framework for how we're going to go about dealing with some of the problems that we're going to see. Okay, this is going to sound silly because I told you that our problems typically show up as word problems, but it seems pretty obvious. But the first step you should think about, if you're kind of thinking about a step-by-step approach, the first thing you should be thinking about is, I know it sounds silly, read the problem carefully. Okay, wow, I can't tell you how many times students will read through a problem and just completely skip over something or misread something or misinterpret something, and it kind of changes how they do the rest of the problem. So read the problem carefully. Step number two, draw a picture. A picture can be really helpful to illustrate specific situations, especially anything with any kind of geometry involved. A lot of our problems are going to be related to physics or just geometry of some sort, some kind of geometrical shape. That could be triangles, circles, squares, rectangles, cones in 3 dimensions, cylinders in 3 dimensions. So drawing yourself a picture can be really helpful to help you set things up. Number 3, I would recommend looking at what values do you know and what do you not know. So what do you know, or what have you been given, and what are you trying to find? Okay, what are you trying to solve for? So what are you solving for? Okay. And this is going to be really good to keep in mind so that you can set up some kind of an equation in order to get to your solution. Okay. The next thing that I would look for in this is actually similar to what do you know and what are you solving for, but in the values that you're given, we're going to see this in a few different specific examples. But with the values that you're given, you'll find that some values are fixed values, means those values are not changing, and some values are changing as time goes on. And so which values are fixed and which values are changing? And keep in mind they're changing with respect to time t. Okay. Number 5, this is going to be kind of probably the most important step that we do, is that once you know what's fixed and what's changing, once you know what you're trying to solve for, set up an equation that relates what you know to what you're finding, or to what you're solving for. Set up an equation relating what you know to what you're finding, or what you're solving for. Okay. Again, this involves triangles. Sometimes that's using a Pythagorean theorem. Sometimes we're using the area of a rectangle. Great, use the formula for the area of a rectangle. Sometimes you need to use things like the surface area of a cylinder, or the volume of a cone, or whatever. But can you come up with some kind of an equation that relates your different quantities in the problem? Okay. Now, once you've set up an equation, then we can get to the calculus part. Okay, by the way, none of this is calculus yet. All of steps 1 through 5 are really just looking at setting up a problem and being able to put variables to things and set up an equation with what you know and what you don't know. Okay, number 6 is where the calculus comes in. So I'm going to move to a new page over here. I hope you're taking notes with me. Number 6 says take the derivative with respect to t. So take the derivative of everything, or of both sides of the equation that you set up, with respect to t. Okay, so I want you to think back for a second about when you took pre-calculus. Okay, in pre-calculus, somewhere at some point you probably talked about, or you should have talked about, something called parametric equations. Do you remember parametric equations? With parametric equations, we had to set up some equation that said x equals something with a t in it. Basically, x was a variable that we could think about as having t as an input variable. And y was a variable that we could think about as having t as a variable as well. And so when we set up parametric equations, we had an x of t equation and a y of t equation. I want you to think about these this way. And so when you think about taking the derivative up here, the derivative is really the derivative we should be thinking about is like a chain rule up here. So you could throw in here, if you wanted to, think about kind of a chain rule where t is your input variable. Okay, because we're so used to thinking about x as the input variable that when we take the derivative of x, in these problems, the derivative of x is not just going to be 1 like it has in the past. The derivative of x is going to be dx dt, because we're taking the derivative with respect to t. Okay, once you take the derivative of both sides, then you can plug in what you know. And solve for what you want. Okay, so plug in what you know, solve for what you're looking for. And then I would just throw in a step number 8 because I mentioned this earlier. But once you've solved your problem, I would say write your answer or write your solution in context of the original problem. Remember, you're thinking about it in a business context. Your boss comes to you and says, could you solve this problem for us? You don't go back to him, you just take the math to him and say, here's the math. You go explain it in using a sentence or two, or in complete sentences, using language that he'll know and understand and can relate to using the correct units. So that's what your answer should look like. Okay, so before we look at some examples, we're gonna have another video here in just a minute with a few different examples with real-world contexts. But before we do that, I want to just look at an example. First of all, I'm going to go back to here this little diagram about solving problems. The first problem that we're going to look at is really just going to involve these bottom two parts. So, so this first problem we have is just going to say set up the math problem and solve the math problem using the derivatives with respect to t. So our first problem is going to look like this, and then the next video is going to have a few different problems that have real-world contexts. Okay, so here is a typical related rates type of problem that we could have that just involves taking a derivative with respect to t. Let's say, for example, we have something like this. This is an equation that I'm going to just give you from the beginning. X squared plus 2y squared equals 5. This should feel a lot like back when we did implicit differentiation, where I'd say take the derivative of both sides and find dy dx in it. But this time it's not dx, it's dt. So go ahead and take a second, or you can hit pause on this video and take the derivative of both sides of this equation with respect to t time. Okay, maybe you pause the video. It should look something like this. And again, you can think about it as a chain rule. If you want to put parentheses around x and parentheses around y, so that you remember that those are both in terms of t, it's x of t and y of t, here's how you can take the derivative of both sides. It would look like 2x, but then not just 2x because it's with respect to t, it's dx dt, and then plus 4y times dy dt, and then equals 0. Derivative of the constant on the other side is always 0. And then let's say at the beginning, I guess I didn't give you directions, but let's say the directions at the beginning said something like this. Find dy dx when x equals 1, y equals 2, and dx dt equals, I'll say 3. Okay, so this says that dx dt is 3, whatever your units are there. Maybe it's miles per hour, maybe it's feet per second, but x is changing by 3 as t changes by 1, and that's specifically at the time, I should say at the point when x is 1 and y is 2. So if this is what you're given, you're told to find dy dx when x is 1, y is 2, and dx dt is 3, then go down here and plug in what you know. Remember, we're kind of walking through the steps, and so this is kind of like, if I go back over to the steps, this is kind of like steps, we started with step 5 that says have an equation, and then we've been working through steps 6 and 7. 6 and 7 say take the derivative of both sides with respect to t, and now plug in what you know. So 2 times 1 times dx dt, remember dx dt is 3, plus 4 times 2 times dy dt, that's what we're trying to solve for, equals 0. And now solve for dy dt. So let's see, this is 6 plus 8 times dy dt equals 0. Subtract 6, divide by 8, or that means that dy dt equals negative 6 over 8, or negative 3 over 4. Okay. So what do you know? What are you looking for? Okay, we're going to have a video coming up that has a few different examples of real-world contexts. I hope you enjoy.